Hello, calculus fans! So in the last video, we talked about this differential equation, dp by dt equals k times p, and it's appropriate for modeling population growth under ideal conditions. Remember, we had an unlimited environment, unlimited food, no predators, no disease. But now we'd like to construct a more realistic model, and often we can't make these assumptions about unlimited resources and no predators or disease. Now usually we'll have limited resources. Now most populations will start off by increasing in an exponential way, but that population growth will slow down when you approach what's known as the carrying capacity of the environment. The environment really can only support so much or so many creatures. So if it's bacteria, there's only so many that you can have in your petri dish before there's just not enough food for everybody. And that's what we'll call the carrying capacity. The environment's limited to being able to carry a certain number of these organisms. If the population ever exceeds the carrying capacity, then it will start decreasing. We're going to make two assumptions for our model. The first is that the population growth is going to be pretty much what it was before. It's proportional to k times the population if the population is small. So that is, the growth rate is proportional to p. We also want the population growth to be negative if the population ever exceeds our carrying capacity. So the population decreases if it ever exceeds that carrying capacity. Now here's an example of a differential equation that will incorporate both of these assumptions. dp by dt is equal to k times p times 1 minus p over m. Now look what happens if p is small compared to m. So if your population is very small and is not near the carrying capacity, then p over m is pretty close to 0, which means the thing that I have in parentheses is pretty close to 1. And in that case, dp by dt is very close to k times p. On the other hand, if p is bigger than m, if your population exceeds the carrying capacity, then now the thing in parentheses will be less than 0, and so dp by dt is less than 0. So the population would then be going down. This particular differential equation is called the logistic equation, and we'll play around with this some more later in the chapter. Okay, that's all for now.